All right, now it's nice as you've done here to include a data table, kind of a summary data table. This doesn't make much sense, however. Having that out to three places, that out to four, and that out to a gazillion places. Sig figs were not have never been in physics particularly concerned with them. Well, some physics teachers would be, but on the other hand, it doesn't make sense to have different numbers of them. And to some extent, your sig fig choice should be made based on your uncertainty. So if you're, if the uncertainties in this is out to the hundredth place, then you probably shouldn't record any digits past the 100th place. All right, but again, the main thing of the results is it looks like your data actually has a pretty good fit functionally with that math function, and probably with a proper derivation of the model for this situation, though it may differ a bit in terms of magnitude, but the sort of functionally the shape looks to be about the same. All right, let's go on to the factors affecting results and discussion of results section. Here again, you choose to make some explanations about what's going on in the data, an excellent thing to do. Again, down here, and a reference to Appendix B where we can see those friction force graphs. This statement I want to point out is a true statement, but it doesn't really explain what's going on. It's true that in general it takes more force to accelerate an object than to keep it at a constant speed, but the static friction force is generally bigger than the kinetic friction force, in part with how those friction bumps on the top and the bottom of the objects that are sliding, how those things interact. And so it's not really so much of a relationship to the force acceleration deal. All right, so in the factors affecting results section, I mean, clearly the coefficient of friction is the major culprit here. Um, your discussion about dust on the table and all is plausible, but as you say, um, it's probably pretty minuscule. Well, actually, that's referring to the inconsistent pull of the string. But anyway, the friction and all, it's challenging to measure that. So that's a pretty, you know, the coefficient, measuring the coefficient of friction is a pretty important source of uncertainty. Whether this is what makes that hard to do, I'm skeptical, but certainly it plays some role. Now, you get your experimenter's best attempt to keep the tension and angle constant. So yeah, I mean, I think your group did take pretty careful data there, or as careful as you could. One thing that's been done in the past that's kind of neat in terms of how to approach this is to rig up a pulley and then pull over the pulley. And the neat thing about that is that once you set up where the block is located, the pulley up on some kind of stand, that pretty much defines this angle. And it allows you to make sure you're pulling at exactly the same angle each time. Because once that wraps around the pulley, it doesn't really matter too much which way you pull here. It'll always be directed from the block like that. So that's a neat way to sort of overcome those sources of uncertainty. Instrument resolution, it's pretty good. It's a pretty good instrument scale. So you have some fluctuations like this. The larger concern is that it's miscalibrated. Okay, miscalibrated. In other words, if it claims it's reading 0 but it's not really reading 0, then that's going to be a bigger source of uncertainty and could dramatically influence not only your results in the experiment per se, but in your calculations of the coefficient of friction.